Test. We can now start. Hello everyone to our ITC Colloquium this week. Our speaker today is Rahul Kannan. He's an assistant professor at York University in Canada since 2023. He got his PhD in 2014 at MPIA in Heidelberg, was then for 3 years with Mark Vogelsberger, a postdoc at MIT, and then until he moved to Canada, first a Hubble Fellow, and then an ITC Fellow at the CFA. He's mostly working on simulations from the local ISM to large-scale structure formation in cosmological boxes, and especially now on the impact of radiation transport in the epoch of reionization. And
thank you for giving me this opportunity to talk here. So as Oliver mentioned, I think most of you in this room know me because I was here till 2022. I'm now an assistant professor at York University, and I will talk today about modeling high-redshift structure formation and reionization, especially in the JWST era. I will start with basic introduction, which I always try to do, which is trying to understand what cosmological structure formation is. So we know the initial conditions of the universe from the cosmic microwave background. The initial density fluctuations were imprinted on the CMB. And so using the CMB, we can get the initial conditions of the universe. And we basically see the density fluctuations are of the order 10 to the minus 5. Whereas if you go to the current universe, then you find much more complex structures that are seen today, galaxies, stars, planets, et cetera, et cetera. And then if you just do a simple calculation, you'll see that the density contrast is of the order 10 to the 5. So you have 10 orders of magnitude change in the density contrast from about 380,000 years after the Big Bang to the present. And this kind of transition takes place mainly through gravity, which is, of course, the main force which causes structures to collapse. But then you have additional forces like radiation, magnetohydrodynamics, star and black hole formation, feedback, et cetera, which also sculpt the properties of all the structures that we see today. So in this specific talk, I won't talk about the whole timeline of the universe. I'll try to focus on two major epochs, which is cosmic dawn, which is basically the first time the universe started forming structures, started forming the very first stars in the universe. So after the cosmic microwave background, the universe went through a period of dark ages where you basically had no structures, and so no light from stars. And then cosmic dawn is when you have the first stars starting to form in these initial protostructures or proto-galaxies, and they start emitting light and begin ionizing the low-density gas around them. That epoch is somewhere between 30 and 15. These are not exact values, but somewhere between 30 and 15 is where cosmic dawn is. Next is epoch of reionization, which is the stage which comes after cosmic dawn, because this is the stage where you have a lot of structures beginning to form in the universe, and they start emitting a lot of high energy radiation. And for the purposes of just hydrogen reionization, we care about photons with energies greater than 13.6 electron volts, which is the ionization potential for hydrogen. And these first stars and galaxies and maybe even black holes, the initial black holes, the radiation from these sources basically ionize the neutral hydrogen in the universe and cause a phase transition from a cold and neutral gas to a hot and ionized medium. Okay? And so these two epochs, cosmic dawn and epoch of reionization, are really important because they form this intermediary link between what you see in the CMB and what is observed today. So if you are able to study structure formation in these two epochs, I have to press this properly. Okay. If you can study structure formation in these two epochs, then you can try to get an evolutionary link between the initial and final stages of structure formation. So that's why it's important. Another reason it's important is because we have entered an era of instruments capable of detecting a lot of galaxies in this epoch. So the first thing is we moved from Hubble, which was quite good, to now JWST and even ALMA. So Hubble could not really detect rest frame optical emission from these very high redshift galaxies. But JWST, because it has much greater mirror, much better resolution, and it is an infrared telescope, you can actually detect galaxies. I'll come to it, but now there are claims of detection up to redshift 30 or so. Okay, so that's why so since we are detecting a lot of we are getting a lot of information in this epoch, it is the right time to study this epoch as well. Okay, the next thing is mapping the IGM has also improved quite a bit. So previously, the IGM used to be mapped using quasar absorption lines, or so you have a background quasar, and this quasar light goes through the IGM, and as it goes through the IGM, it creates kind of like a Lyman alpha forest, which is and you study the statistics of this Lyman alpha forest to actually figure out the state of the intergalactic medium in the universe. But now with new instruments like HERA and even other instruments like SPHEREx, you can actually do intensity mapping. So basically you are trying to map the IGM not in absorption like in quasar spectra, but you are actually mapping this IGM in emission. That's the idea. So you go from a picture of an IGM, which was just the properties along skewers, to actually a tomographic map. That's the whole idea of doing 21 centimeter intensity mapping. Not just 21 centimeter, here I'm just showing 21 centimeter, but SPHEREx, for example, tries to do other emission lines like H alpha, Lyman alpha, et cetera, et cetera. So in both cases, we are getting to the point where we can map not just the galaxies themselves, but also the ionized IGM around it, or just the IGM around it, not just ionized. So you can map the galaxies and the IGM together, and you can study this reionization process in great detail. Okay, so there is a need to have efficient models which can accurately interpret all these observations that we are going to see. Okay, and so JWST came along, and it has produced a lot of surprises. So on the left here, I show an image or a plot from Mike Boylan-Kolchin, who showed that if you just take these JWST observations kind of at face value, and you try to see what is the star formation efficiency in halos that you need in order to describe these huge, very high stellar mass galaxies at redshift 9. What you get is basically that you need efficiency, baryon conversion efficiency close to 100% in order to explain these galaxies. So this gray line is 10%, this is 32%, and this is 100%. In the low redshift universe, it's close. It's between this gray and these orange lines. But it seems for these massive galaxies detected by JWST, you need to convert almost 100% of the baryons in the galaxy in order to explain this. Okay. There have been claims that this is not really true. There is contribution from AGN, et cetera, but still a very interesting result.
If you take population 3 stars, that makes
Yes.
it much better.
Yes, if you change the IMF, it comes down quite a bit. Yes. Yes.
So when you say 100%, is it the baryons inside the virial radius?
Yeah.
100% of the virial.
Yes.
No, but that's for normal stars. If you take pop 3, then you bring
Then
it
you
down.
can bring it
Yeah,
down.
yeah.
That's the way to do it.
Yeah, so if you have a top heavy IMF, POP3 or through something else, you can definitely bring it down. Okay, so that's on the left. On the right, you can see there have been papers like in the last 2-3 months or so, claiming measurements of UV luminosity functions at redshift 20 to 30. Okay, so these are just upper limits at redshift, I think 28. But there's this another paper, Perez-Gonzalez, which measurements at redshift 25. I'm not an observer. I'm not going to critique this work, but this is what exists. Okay. Okay. Next, the JWST has also detected ionization bubbles around like a redshift 13 galaxy. Here is a redshift 13 galaxy. This is a very nice spectra from JWST, not just photometry. It's actually spectroscopy. And they detect a Lyman alpha line with an equivalent width of like 40 angstroms. And the only way you can prevent the complete extinction of this Lyman alpha line is if there is an ionized bubble around this galaxy, which helps this Lyman alpha line escape. So you're actually able to detect the onset of reionization around these really early galaxies as well. Okay. The bubble size? I don't remember.
Probably a few
Yeah.
megaparsec.
Yeah, probably. Yeah. Okay, so it has. So the upshot of all of this is that it has been an exciting few years, and people in the press have run with it, and it's quite nice because it gives us. It's a very interesting field to work in right now. Okay, so let's shift to actually modeling these modeling galaxy formation. So galaxy formation is a complex multi-scale, multi-physics problem. It generally requires the solution of complex physics like a couple physics like gravity, hydrodynamics, star and black hole formation, feedback, so feedback from stars and black holes. I would argue self-consistent radiation hydrodynamics, dust, accurate source dust, and what I mean by source functions is how much amount of radiation these stars and black holes put into the environment. That is also important. Okay. So as a caveat, I will just say that in most cases, and not in all simulations, but in most simulations, most of these processes occur on a subgrid scale. So here is an example. I mean, not an example. Just a simple illustration of what I mean. So most of the times, the smallest grid scale of a simulation is of about a large scale simulation is about a kiloparsec or so. But if you look at on what radii the supernova feedback bubble or like the Stromgren radius around a star exists, that happens on like parsec scales. Okay, so the important physics that is going on around star formation and feedback happens on scales which are much smaller than the grid scale of the simulation. And so almost all models require some kind of a subgrid model, a subgrid physical model in order to capture this physics. Okay, so that's a caveat, and I'll come to this at a later point as well. And so the simulation landscape is quite rich. There are a lot of simulations, a lot of different simulation codes, a lot of different models for galaxies. Here is a different simulation set that in the review paper by Mark. And interestingly, it can be said that wildly different subgrid models, models which model this feedback process in a very different way, all give rise to very similar galaxy properties, at least at redshift 0. Okay, because the matter of fact, they're kind of tuned to get the properties at kind of redshift 0 correct. Okay, and one of the most important properties that simulations try to match is this kind of star formation efficiency within a halo, or basically the stellar to halo mass relation, as it is called. So you're plotting the stellar mass as a stellar mass to halo mass as a function of peak halo mass of the halo. And so the efficiency with which you can, not the efficiency, the amount of stars in a halo is about 1% of the halo mass. Here is 1%, so it can be about 2, 3 more as well, or 10%. It cannot go up to 10%. So it usually goes up to like 5% for the Milky Way, and it's lower for less mass halos and lower for even higher mass halos.
The amazing thing is that it's independent of redshift.
There's a slight redshift dependence, but yes, it seems to, well, this was pre-JWST, and it seems to be independent of redshift. Okay, yeah. So the idea is that star formation in halos is inefficient. That's the whole point of this plot. Okay. Okay, so that was about structure formation. What about reionization? So we did not talk about reionization in these. Most of these simulations do not really capture the reionization process. And the reason is that they do not have self-consistent radiation hydrodynamics. So you cannot really model how the radiation field interacts with the surrounding IGM and creates this patchy reionization process in general. And reionization itself is also quite complex because more, as you know, stars and black holes are the ones which are producing most of this radiation. And they produce this radiation on, let's say, sub-parsec scales, let's say. This has to propagate through the ISM of the galaxy on kiloparsec scales, then transmission through the CGM on hundreds of kiloparsec scale, and finally get into the IGM in order to reionize the universe. So it's a complex, so if you want to model the whole thing, it's kind of impossible, right? Because you're going from really small scales to the really big one on a computer. Okay, so I talked about structure formation, I talked about reionization, and we wanted to do this properly. And so I did this work here at Harvard, where we developed these THESAN coupled galaxy formation plus radiation hydrodynamic simulations, which can potentially model both the reionization process and the galaxies and stars which are responsible for it. So in this image, in the background image, what you're showing is the, as a function of time, this is high redshift, this is low redshift, the evolution of the temperature of the IGM. And you can see that initially you have mostly, it's a cold universe, and then you have these hot spots around galaxies, because this is where the radiation from the galaxies is heating up the surrounding IGM. As you go to lower and lower redshifts, these ionized or high temperature patches merge with each other until by the end of the simulation, which is redshift 5.5, you have a fully ionized universe. And the good thing about THESAN is that you just don't model the background process. You can also model the properties of the sources. So you're zooming in on one particular galaxy here. This is a mock JWST image. This is a mock ALMA image. And you can actually see the properties of the sources of which are responsible for this reionization process. Okay. So how do we do this? We take a very well-tested model which works really well, which is this Illustris TNG model. And we know that it works very well, extremely well, down to redshift 0. And then we couple it we couple it with the radiation hydrodynamics code, or REPO-RT, which can handle a large number of sources quite efficiently. And then we run this together to perform these simulations. And we kind of showed that we get the accurate reionization properties. So on the left is the neutral fraction evolution as a function of redshift. And this was tuned. So we had a parameter to get this reionization right. Well, well, at least go through the observational points which are all over the place. So that's not really a prediction, but on the right is a prediction which shows the evolution of the mean free path as a function of redshift. So mean free path of ionizing photons, how far an ionizing photon travels before it gets absorbed by some neutral region. And so previous expectations were that the mean free path evolves very, very shallow. The evolution is quite shallow. But then we got a very strong evolution of this mean free path, very steep evolution of this mean free path, and recent observations kind of tell us that this steep evolution is the right way the universe behaves. And the reason we get this right is we think we have a late reionization process, and also we are able to resolve the sinks in the IGM that are important to get the mean free path correct. So that's the reionization. We also get kind of the pre-JWST stellar efficiencies in halos, right? Okay, so on the left, I'm again plotting the stellar mass halo mass relation, the one that I showed before, and these the black lines are these THESAN points, and the blue lines are the relation from Behrouzi that I showed before. And we kind of get that right. So we have inefficient star formation in most of these halos. We also see that the star formation rate in these halos drops off. So at redshift, so this is on the y-axis is the star formation rate density in the universe. So and the black points are these pre-JWST estimates for the star formation rate density. So it went only up to about redshift 9 or so. And then we see that it kind of drops off quite quickly. So we kind of matched what pre-JWST observations told us, which is not surprising because we use that illustrious TNG model which performs quite well. So one other application of these THESAN simulations is that we can also, because we model the galaxies and the IGM together, we can actually try to connect which galaxies are responsible for what kind of bubbles or what kind of ionized region around it. And so here you can see, this is like a Lyman alpha transmission curve, the same way you do for a quasars. So you imagine you have a background quasar, and blueward of the Lyman alpha line, everything will be observed if your universe is neutral, right? But if you have some ionized region around the galaxy, you get these transmission spikes. And these spikes corresponds to ionized regions around the galaxy itself. So, and this is what is shown here as well. This is like a mock skewer along a line of sight in the THESAN simulation. And we can actually say, okay, this spike here corresponds to this galaxy ionizing the region around it. This spike corresponds to this galaxy ionizing the region around it, et cetera, et cetera. So how do we do this quantitatively? What we can plot is the average or the mean transmission of the Lyman alpha line as a function of radius from the galaxy. Okay? So on the y-axis, you can think of it as a mean transmission. So if it is 0, that means your Lyman alpha transmission is equal to what is the mean transmission in the universe. If it is above, then you have more transmission compared to the mean transmission, and if it is below, it is less than the mean transmission. Okay? So close to the galaxies, you have lower than the mean because you have a lot of cold, dense gas, which is not ionized because you have a lot of inflow from this cold, dense gas and the ISM of galaxies. If you go in the intermediate distances, then what you see is that because you have an ionized region around this galaxy, your Lyman alpha transmission is enhanced because you have this ionized region around it. And then as you go to very large distances, it just becomes mean Lyman alpha transmission values. Okay? And so that was pre-JWST. You saw this result. And this was confirmed by JWST observations, which show that you see this kind of a behavior as well. Low transmission close to the source, a higher transmission at intermediate distances from the source, and goes back to the mean at very large distance.
That's going out to tens of megaparsecs?
Yes, yes.
A single galaxy can do that?
Yes, at later stages. So these are later stages of, you see it's reionization So the redshift here is 5.86, so it's almost at the end stages of reionization. It's not a single galaxy. I would say it's a bubble around a galaxy.
There are
Clusters of galaxies.
And there are also large-scale structures in the filaments, and
Yeah.
so that introduces correlations.
Yeah, exactly. Yeah. Yes.
So close to the galaxies, is it just ionized bubble or also winds? Because
The winds can also
help.
Sure, but not on these big scales, right? Tens of megaparsec scales.
You know?
Here also you see it's 10 to 20 megaparsecs. So on these scales, it's mostly just radiation.
There is not enough time for the wind to go that distance at that early time.
Right.
You just take the typical speed of a wind and multiply with the age of the universe, it will give you less than a megaparsec at that time.
Thank you. Yeah, and so yeah, that was a good result. And then we can also calculate the bubble size evolution, and so this red curve is the bubble size evolution. So as a function of neutral fraction, as you get to higher and higher, lower and lower neutral fractions, your bubble sizes keep increasing. And the theoretical curve from Furnale to NO is given in the black line. So we are actually very close to the theoretical curve. So, and most importantly, JWST also has measurements of these bubble sizes around individual galaxies using the Lyman alpha damping wing. And this is what they get. So at high neutral fractions, we kind of match it if we say that we can only see bubbles around bright galaxies, because there is a selection function involved when you're looking at bubble sizes around galaxies. You can only see these bubbles around bright galaxies. So if you make that selection, then yes, you're biased towards larger bubble size values. So you do get kind of match what they say. But they seem to indicate that the bubble size increased quite rapidly. Either something is wrong with what we are doing, or they are overestimating the bubble sizes. And so there are papers saying that they should actually come down. But anyway. And the other thing we can do is also, because this is a large volume, we can also make predictions for 21 centimeter maps and these 21 centimeter line intensity maps, which is shown on the top, and even H alpha line intensity maps, which is shown at the bottom, and try to figure out if you can differentiate between different reionization scenarios. So this is the 21 centimeter autocorrelation power spectrum in a reionization scenario where only small galaxies contribute to the reionization process. That's the blue line. And the red line if large galaxies contribute to the reionization process, and you can see there's a difference. And you can make that kind of estimate even in the cross-correlation power spectrum. So you're cross-correlating the 21 centimeter line and the H alpha line. And where the cross-correlation goes from positive to negative, this kind of transition scale, that will change depending upon what galaxies are providing the main sources of reionization as well. Okay. Okay. So these were all kind of pre-JWST estimates. Then JWST came along, and then we tried to figure out what it is actually telling us. So this is the UV luminosity function at redshift 8, 9, and 10. The black points are HST estimates, and the red points are, so this is 2-3 years old, so we have a lot more data now. The red points are JWST measurements, and you can see that they kind of agree at redshift 8, redshift 9, redshift 10 as well, but the model does not agree at kind of redshift 10 at the high masses. But if you assume that these very early high mass galaxies do not have dust, then you're still okay. Okay, but by the time you go to redshift 11, 12, 15, you're way off. Okay, so the model predicts too few massive galaxies compared to what JWST is seeing. Okay, yeah, too few luminous galaxies compared to what JWST is seeing. Okay. And so this is another way of looking at it. This is the surface density of galaxies above a certain limit. Oh, there's the limit, magnitude limit. And the gray area is what JWST observes. So this is the Sears estimate. And all these different models are different simulation or semi-analytic models plotted in the same plot. There is one maybe here. We don't really know how it behaves, but most of them are below this estimate from JWST. Okay, so there is definitely a problem here. Especially, so by the time you reach redshift 9, you're kind of okay, but at high redshift, you're just way off. Okay, so there are a lot of potential solutions. Some are cosmological in nature. For example, I won't go into too much details. There have been papers talking about primordial black holes fixing this, early dark energy fixing this, even cosmic strings fixing this. But there are also potential astrophysics solutions. So one solution that Avi already talked about is variable IMF. So what you're actually seeing here is the light from these galaxies. You're not really seeing the mass. Mass is a derived quantity. And in order to derive the mass, you have to assume some kind of an initial mass function. So if you assume a standard local initial mass function like Salpeter or Chabrier, there is a problem. But if you can assume, if you can figure out a way that you have preferentially top-heavy IMF in these high-density, low-metallicity environments, then you can actually, you don't need a lot of mass to get that much light, and you can kind of explain away what JWST is telling you. Okay, so that's one potential solution. The other solution is that the feedback itself is inefficient. So there are papers like Avishai Dekel's paper who claim that in these very high density regimes at very high redshift, the free fall times on these star forming gas clumps is so short, 1 million years or so, that none of the feedback processes has the time to disrupt this cloud, and it just collapses and forms stars. There's also evidence from numerical simulations that if you have a very high cloud surface density, then especially at densities greater than 10 to the 4, 10 to the 5 or so, what happens is that so you only have a certain amount of momentum you can inject from these stars. At these very high densities, the gravity is so strong that none of these feedback processes can do anything. It just collapses and just forms stars. So the cloud scale star formation efficiency starts to become close to unity. Okay. So we want to test if some of these things are true. And for that, we went and we tried to do a different set of simulations called THESAN zooms. And the reason for that is one of the model choices for illustrious TNG is because we do not have enough resolution. We consider the ISM to be in an effective equation of state. So although you get the global properties of the galaxies correct, it cannot really tell you something about the dense cold phase of the ISM that is in these galaxies. So we went and we tried to improve this model, and we call this the THESAN zoom model, where we have better low temperature cooling, which follows non-equilibrium thermochemistry and molecular hydrogen. We have this H2 formation and dust grains, and because it is coupled to radiative transfer, we can look at the ionization states and photodissociation regions. And what this does, sorry, before I go there, is it takes, instead of putting the ISM in an effective equation of state here, you actually get this multi-phase ISM structure in these galaxies. So you can say a bit more about how these processes are going on. So we took like 14 galaxies from the main THESAN volume, and we re-simulated it at a much higher resolution with this multi-phase ISM model. And so we can try to look at how these kinds of feedback mechanisms behave. In addition to that, because these galaxies are taken from these large volume simulation, we can not only get the large scale structure, which is the large scale matter distribution, we can also get the large scale radiation distribution around these galaxies. So we can take the radiation field, which is given from these large scale THESAN simulation, and put it into this, inject this radiation in the boundary layers of this THESAN zoom model, so that you can actually follow the outside-in reionization process which happens in these low mass galaxies. Okay, And this is important because it leads to realistic reionization histories and more accurate neutral fraction and temperature evolution, especially in these low mass galaxies which are externally reionized. So what I mean by that is you can see, for example, this temperature evolution in a low mass galaxy. If you assume like a flash reionization, which is what is assumed in many cosmological simulations at redshift 10, then the temperature of this halo increases immediately to 10 to the 4, and then it stays there. Whereas if you have self-consistent reionization, which is in black, then the temperature increases much more slowly. So the halo does not evaporate as quickly. And you can see in this very low mass galaxy that this kind of temperature evolution is really important, okay? And this has impact for like how much POP3 stars you can form, for example. So if you have these very late or patchy reionization process, then you can have these mini halos which can only reionize down to after which are evaporated only after reionization process is finished. So you can keep forming these low metallicity stars, which we here put it as POP3 stars. You can keep forming these low metallicity stars from this pristine gas down to redshift 5 or so. But instead, if you put like a reionization model which reionizes quite early at say redshift 9, then you photo-evaporate all these low metal enriched, low mass halos, and you stop forming stars, low metallicity stars immediately. So if you want to understand how the population of these stars, then it is important to get this reionization process right in these halos. Okay, so as I said, these are a set of simulations, zoom simulations, and so the first thing we can test is how efficient star formation is in these halos. And here again I plot the stellar mass, halo mass relation, the usual thing. At redshift 3, 4, 3, 5, 7 or so, we kind of match what pre-JWST estimates are telling us. But by the time we get to redshift 11, 13, or 15, we are slightly higher. Our star formation efficiency in these THESAN zoom halos seem to be slightly higher than what people expected, okay? So that is seen in this UV luminosity functions as well. So the blue lines are these from these pre-JWST Millennium TNG estimates, and the black lines are these THESAN zoom estimates, and all the points are like orange points are observational estimates. So we kind of match, at least at the high mass end, at low redshift. At high redshift, we are higher than what previous models estimated. But we still, because it was still a small sample, we do not really go to the really luminescent, not massive end, really luminous end of this UV luminosity function. Yes?
Talking about the massive end, you don't go beyond into the 12 halos, right?
Yes.
In the pictures you showed. Is it that they don't exist at those redshift, or
Our box
JWST doesn't look at them?
Our box size is only 100 megaparsec, so they don't exist at those redshifts. We are now trying to get galaxies from a 750 megaparsec box, and hopefully, not hopefully, we know they exist at those redshifts, and we will perform those simulations.
Then you have to worry about the AGN feedback.
Yes. That we haven't worried about.
You haven't worried so far, okay.
There is also the issue of cosmic variance, because
Yes.
they are very clustered,
Right.
and so you may get a lot of them in one box and
Yeah.
nothing in others.
Sure.
Yeah.
Yes, that is also true. So we are hoping at 750 megaparsec it's still not that bad, but we don't know. Yes. So again, this is similar kind of plot. As a function of redshift, you are plotting the star formation rate, surface density. Not surface density, just the density, star formation rate density. And you can see that like the previous models are here, and we kind of slightly higher. So the question is, why do we tend to do slightly better than what previous set of simulations did? So for that, we looked at the halo scale star formation efficiency, which is just defined as the star formation rate divided by the baryon fraction times the halo accretion rate, as a function of the halo mass. And what people generally assume is this dot dash line here, That's the kind of Bernoulli kind of relation, the abundance matching relation. And what we get in these zooms is slight higher star formation efficiency per halo mass, so about 2 to 3 times higher. And we seem to have this kind of a shape where initially it's halo mass of the halo power 2 by 3, and then it falls off as mass to the halo 1/3. So we have slightly higher star formation efficiencies. And we see that in the Kenniket-Schmidt relation as well. At low gas surface densities, we kind of match the low redshift values. So that, well, our gas depletion time is of the order 1 to 10 gigayears. But as you go to higher and higher star formation efficiencies, higher and higher gas surface densities, your star formation rate surface density also increases, and your gas depletion time can become as low as 0.1 gigayears. And the idea is that the increased star formation efficiency in these high mass halos is mainly because they have higher gas surface densities. Okay, and they actually follow this kind of a relation, which is sigma, the gas surface density to the power square, which is expected if turbulent energy dissipation in the ISM is balanced by energy injection from stellar feedback. Looking at it even a bit more, we can also try to figure out why you get these low gas depletion times at high surface densities. And so what we are plotting here is on the top, the depletion time. In the second panel, it's the fraction of the ISM that is in GMCs. The third is the efficiency of star formation in GMCs per freefall time. And the fourth is the freefall time of the GMC itself, as a function of the gas surface density. And as I showed earlier, the gas depletion times keep reducing as you go to higher and higher gas surface density. So this is the same effect that you see here. And what we actually see is that the efficiency for pre-fall time and the free-fall time varies a little bit. So you should just look at the red and green plots, green points. Varies a little bit, not too much. So it's kind of constant. So the efficiency for free-fall time just slightly increases at very high surface densities. That is expected because your GMCs are much more massive. Your free-fall time slightly decreases because, again, your GMCs are much more massive. But the main factor which leads to this increase in these star formation efficiencies is actually the fact that much more of your ISM is in the form of GMCs. It's much more clumpy. So when you go to high gas surface densities, it's much more clumpy. It's a lot of the gas is in this clumpy GMC kind of a medium. And this increase is what causes this higher star formation efficiencies at high gas surface density. In this model, there are different models which make different kind of predictions, but in this one, this is what we see. Okay. Yes.
Isn't it like a fixed parameter in the model? So why?
It is, but you actually calculated how long it takes for the GMC to destruct. Kind of thing.
Okay. And what are the different color?
So the blue one is without any. So we have a additional mode of feedback called early stellar feedback, which was necessary in order to get the right stellar masses. So if we don't inject that energy, our efficiency is higher, which is expected. Okay. And so what is the implication for this UV luminosity function? This so you can use like an empirical model to try to figure out if this increased efficiency can actually explain these observations at high redshift. And so the red line is the efficiency that we see from THESAN zoom simulations applied to this empirical model, and the green line is the previous efficiency that we assumed in previous works. And you can see that we can actually, at least part of the data can be explained by this increased efficiency. And at redshift 12 at least. By the time you reach redshift 14, even this increased efficiency cannot really explain what JWST is telling us. Oh yeah, this line does not just include an increased efficiency. It also it includes a moderate level of burstiness. So you need to include a little bit of burstiness in this UV luminosity in order to match these observations. And the question is, do we actually see this increased burstiness in these simulations? And the point is, we do actually see an increased short-term burstiness in the star formation rate as you go to higher and higher redshift. But that does not seem to translate too much into this sigma UV because the UV kind of tracks the long-term burstiness. So it does not really track too much. But again, caveat, at high redshifts, we only have galaxies with stellar masses up to 10 to the 7.5 or so. If you really want to look at this massive regime, we have to perform simulations of massive galaxies in order to make much more concrete predictions for this. Okay, so just to have more discussion, I'll try to conclude here. JWST observations have thrown up a lot of surprises. The models that worked at low redshifts seem to fail in these high redshift environments. That's not surprising because it's a fundamentally different environment with high gas fractions, low metallicities, and a lot more mergers. Variety of both astrophysical and cosmological solutions have been put forward. I'm not claiming one or the other is the definitive answer, but it's a good time to work on this subject now. And so THESAN and THESAN zoom simulations provide a theoretical framework to interpret these results, and a lot of work needs to be done. So for future work, we are trying to run larger volume reionization simulations called THESAN XL, which Oliver is the PI here. We are trying to run much more massive galaxies in this high redshift regime to extend the UV luminosity functions in the observed range. We are also trying to do some star-by-star simulations and also include models like POP3 feedback, POP3 star formation feedback and enrichment. And that's what I'll talk about during the ITC luncheon. So thank you.
Yeah, thank you very much, Rahul. Do we have any questions?
So what is the contribution from supernova? Because if you have a supernova that lasts in the rest frame, let's say a few weeks,
Yeah.
it will be stretched by a factor of, 20 at redshift 15 or
Right.
even more. So that would be as if it's a steady source for us. We would not see that it's a transient.
Right.
It would overwhelm the luminosity of the galaxy. So my question is, how do we know that this luminosity function doesn't have a contribution from transients?
Good point. I don't know. Is there a way to decouple this in observations?
From the spectrum, I don't know, but it's something that
Yes.
we should think about, I guess.
Yes, especially if you're looking at the same field after some amount of time, maybe you can see
Maybe
the
after a
difference.
decade.
Yeah.
But it's really stretched by
Right,
so
right.
it's not the standard transient.
Right. Yeah, I agree. Yeah. It's a good point. I don't know the answer. Yes.
So in reionization, there are like two guardrails, right? Well, basically the photon budget, and you can decompose that into the mean free path and the hydrogen photonization rate. So I saw that in your models, what THESAN's predicting is like perfectly fine with the mean free path, but how about hydrogen photonization rate? Does it like satisfy the Lyman alpha forest constraint or?
It does up to 5, and then it overshoots below redshift 5. So there it goes well. It matches observations up to, I don't have the plot. It matches observations up to redshift 5 or so, and then it kind of overshoots what was the gamma H1.
So have you taken any kind of confidence? Because I was also having the same problem, and when you take the confidence actually brings it down.
Sure. Also, the escape fractions might be much lower below redshift 5. That is something we cannot know, at least from these large-scale models. It's difficult to get it right, the escape fractions as a function of.
There are in observational, you have galaxy escape fraction of 3 to 20%, not super crazy escape fraction. So you use one of the distributions and use that mean or 16% or 84% or what?
What do you get?
Yeah, basically what you get.
The stuff up. So here's the problem, right? I mean, if it is a constant escape fraction per galaxy, irrespective of what the mass of the galaxy is, the high mass galaxies start to dominate and your star formation rate starts to dominate and it will always shoot up. It will never flatten out like what you see in the observations. So if you want to that curve to flatten out, then you need something else like an escape fraction, like a galaxy-dependent escape fraction or clumping, which is somehow different at low redshift and stuff like that.
But escape fraction will be like a variable thing, like time dependent, because like sometimes when you have a first star formation, it will go up and then it will just come down the other times. So maybe having some kind of simplistic model of this.
Yeah, sure. But ours is very simple, so it doesn't capture that.
So I have a reply to Avi's question on supernovae, and then I have a quick question for you. So I think in the real JWST data right now, we are seeing some supernovae that are pop up in 1 year and then fade out in the second year, and their ICD overall look like redshift 15 galaxy. We don't know whether they are redshift 15 galaxy supernovae or redshift 3 that have a Balmer break, but these kind of things probably take 10% of the photometric sample, and it's not a big issue. And if you have multiple epoch observation, you can remove them. And my question is for the matching of the U luminosity function. I think you show a plot at redshift 3, 4 compared with redshift 12. Right now with the THESAN zoom, it seems like yes, this one you are start to match the redshift 12, but the redshift 3, 5, this kind of region, I think they start to get some small mismatch.
Slightly higher, yes, at
So,
the lower mass galaxies. So
dust? Oh.
not dust. So again, we are estimating this in a very crude manner because these are zoom simulations. We have to correct for the fact that they're zooms. It's not a volume, so you don't have a representative sample. And we have done a very, very simple job of correcting this just by assuming that the number density is the same. Now, we haven't done we don't know how to do this really properly, and we are trying to figure out if we do this properly, will this fall back down? That I'm not sure.
Hey Rahul, do you find any difference in, because I assume when you have the effective equation of state, you have to assume some sort of ISM escape fraction or tune something to that effect. Do you find that the escape fraction you get in the THESAN zooms is the same as what you assume? Or how does it, or to put it another way, does the inside-out effect of reionization within your kind of zoom regions, does that differ from the original THESAN implementation?
Yes, the escape fractions are quite different.
Okay, interesting. So
the galaxy production, photon production rate is different, the escape fractions. Okay, so we have estimated some escape fractions. They are in the same range, like 10 to 20%, but that doesn't mean they are the same, right? So for example, this galaxy here, you can see that in the original THESAN zoom, the radiation has already propagated out and it has started ionizing a bubble here in the original THESAN, but in the THESAN zoom, the bubble has only reached so far. It has still not propagated out to these distances. So there are differences in the reionization model, I would say.
yeah, I guess I'd be interested, obviously not feasible to run, but like if you could run a whole box with that, would you end up with?
Yeah, we ran a 5 megaparsec box. I don't know what to say about that.
So regarding the point that most of the ISM is in GMCs at high redshift, so how much do you think the dust attenuation of these UV emission be important?
The dust, because you have a lot more dust in these GMC scales.
And it's confined in very small scales.
Yeah, so if a lot of it is in GMCs, and if you actually form a lot of dust this early in the universe, then the attenuation will be quite high.
So you need a way to like remove the dust.
If you can disrupt the GMCs quite efficiently, yes. If not, no. So there are, I think, models which talk about like the star formation becoming super Eddington and blowing everything out, and it becomes dust-free. These are these Andrea Ferrara's models. That's how they explain these really luminous redshift 14 galaxies. So there are people working on that.
Yeah, then you'll expel the gas as well, right?
Yeah, expel everything out. Yeah.
Great. Any more questions?
Hey, great talk. I have a question about this plot and also about the earlier point about luminosity functions at low redshift. So isn't it like the fact that you have more low mass galaxies at lower redshifts is just through manifestation of this fact that the Helmholtz-Thomas relation is higher? And so it seems that it's something that simulations show in general, that you need to, on the one hand, you need to very high star mass Helmholtz relation early times to explain JWST results, but also it must transition to the Behroozy whatever relation at lower redshifts.
Yes, you're correct. So this, the fact that we get the high mass galaxies right at redshift 3, but not the low mass, was probably because we are here instead of here, even at low redshift. So we are not getting things right. That is true.
Do you have idea like what's
efficiency seems to be higher?
So is there like something? I mean, what I was wondering just what your thoughts was missing. How to create this transition in the star mass Helmholtz relation?
Some physics which works at high redshift but not at low redshift. Lyman alpha radiation pressure, for example. You know, in dust-free environments it works very well, but if you have dust, then you get rid of the Lyman alpha, and then you won't have enough wavelength. That's just one example of what might get this transition right, but I'm guessing here. I don't know.
Great. Any more questions? If not, then we can thank the speaker again. Thank you so much.